And welcome to this video of Laplace Transform. So we're going to do complex exponentials this time. Okay. Complex exponentials. So this is the case where you have the exponentials multiplied with a sine or cosine. But yeah, basically it's like this. I'm going to look at one of these e to the I omega t kind of things. Okay, I'm going to start from there. Yeah, so we don't just want e to the I omega t, we want to have a plus I omega t. Okay, so this is a complex exponential. You can have any so-called combination of such things, whichever you want. So yeah, this is what it is. A plus I omega. Of course you can separate out the exponentials, but I won't for this. I won't. Okay, so this is where both a and I omega are less than 0. Okay, the real part a less than 0. Okay, and I omega or omega less than 0. Yeah, so the real and the imaginary parts are both so-called less than 0. Okay, so we will have this sort of thing going on. And then you can imagine you basically need to do the integral again. Okay, I'm not going to just repeat everything. Okay, I guess I can repeat and copy and paste down. So let's have our limits, which I just want to copy and paste. Okay. This is the limits. These are the limits. Okay, so how do we do this? Yeah, you just substitute. Copy paste, copy paste. So I omega, so it's a plus I omega this time. So okay, you'll be minus a plus I omega, minus a minus I omega and minus s. So all of these will be gathered together. So I have a plus I omega plus s, and then a plus I omega plus s at the bottom. Excuse me. Okay, so after this, very simple. We make the assumption again. Somehow a plus I omega plus s more than 0. Okay, so that as t goes to infinity, the whole term will just drop out, and I will just ignore the first term. Alright, so this is a condition for this whole thing to converge properly. So I will get this minus sign out, and I'll get the minus sign out in the denominator. Okay, minus sign out in the denominator, and then what happens? Okay, yeah, what happens is that excuse me. What happens is that you will just have this thing on top. T goes to 0. T goes to 0, this whole thing at the top will just cancel out. Okay. Yeah. Oh. So I'll just take out the limits. Okay. We went through it many times already, so I'm not going to go through the whole procedure again. Okay. T goes to 0, and this thing will drop out. Okay. This thing will become 1 on the numerator. So you can see it kind of becomes pretty routine. Okay, if you have a negative exponential, you can almost guess it. All right, just by going through the rough steps, because we did exponentials so many times, both imaginary and real. The complex is not so complex, if you know what I mean. Okay, so minus I omega. Okay, so this is the case number 2, omega more than 0. So this is case 2, the second case. So there are 4 quadrants of this S-plane. So this is one of them, this is the second one, and of course choose 2, I think I think 2p2, I think. You just have 4 permutations, okay? 4 permutations of this. Okay, so you will just have this thing over here. You will need to assume so a minus I omega plus s more than 0. Okay, so that's the other case, and these two are pretty much all you need to do to get your excuse me, to get your what do you call it, let's see, a minus I omega t. Yeah, I'll just copy and paste down the integral on top. It's not too much of an issue. Okay, so instead of plus I omega, I'll have minus I omega. Alright, and after you solve for it, yeah, you apply this condition. You will just remove the limits out, remove the minus sign out at the bottom, and the top will just become 1. It's a very convenient thing. Yeah. Okay, so that's how. Oops, not so convenient. Not so good. Okay, there we go. All right. Okay, nothing too difficult. Okay, so this will give you the tools to start for example doing something like this. Yeah. So Laplace of e to the at, e minus at, then sine omega t, for example. Okay. So what will you have? Okay, what will you have? Okay. Left, right. Alright, minus 80. Okay. Yeah, so what's the Laplace transform of this? You'll just find out it's this thing sort of multiplied by the complex conjugate, then you have something on top. Okay. Okay, so I mean, I'll just do one case of the signs. Okay, I'll just do one case of this complex exponential, the sign case, and then the rest you just figure out. You can derive it yourself. So I'll just give you one example, okay, and that's about it for the time being. Okay, hopefully you can figure it out. I'm not going to go through that in depth in detail. If you know the answer, of course, type it in the comments. It'll be great as well. Using whatever format you can have. So what you have is this. Okay, so I'll just convert this into a sum of complex exponentials. So let me put this here. Okay, so I won't be doing I omega t. There'll be e to the at, yes, e to the at, e minus st dt. What is the sine omega t? We can just copy and paste the exponential form of it. So that will be e to the power of I omega t minus e to the power of minus I omega t. Okay, yeah, and then you divide the whole thing by 2i. Okay, so now we have this. Basically, we can split this up into two Laplace transforms, because Laplace transform, it's sort of a linear thing. Okay, there is linearity. Linearity associated with it. Okay, so maybe I'll do it this way. Let's put this whole thing over here. I'll put the sign transforms over here. Okay, that's better. Over here, yeah. So yeah, then you will have a sum of two complex exponentials, and you just divide everything out by 2i. That's how simple it is to Laplace transform these kind of things. Because once you divide them out into exponentials, you sort of know exponentials is almost the easiest Laplace transform. Okay, because of after you derive the first kind of exponential Laplace transform, everything else just follows in a very much similar manner. Okay, so let's do this thing. Yeah, let's do this and see how things go. All right, so this yeah, I have two identical lines for some reason. Okay. Yeah, let's decompose this into two Laplace transforms, which we derived earlier over here. Okay, so we have the first Laplace transform is, okay, we can actually decompose this into two Laplace transforms. So equals to mathcal L. Okay, and we have a fraction 1 over 2i in front, so we don't deal with the imaginary numbers till later. Okay, first Laplace transform is what? E to the a minus at. Okay, so e to the minus at plus I omega t. Now that's the first Laplace transform, and of course we will have minus 2i for the second Laplace transform, because integrals in general, they have this linearity property, so we can just exploit that. And then second Laplace transform, what do we have? Okay, mathcal O, so we have a minus I omega t here. Alright, minus I omega t. Okay, so conveniently enough, we already derived everything beforehand, so we can just substitute the expressions in. So what are the expressions for e to the minus at plus I omega t? So where is this a is less than 0, omega is more than 0. So this is the second part over here. So I'll just copy and paste this Laplace transform over here. Okay, let's see. Okay, so we can apply this to sines and cosines with exponential product. So these are decaying sine wave. Okay, very simple. So let's see. Where is it? Here. My goodness, it's too much code. Okay, so the first Laplace transform will be this thing here. Okay, first Laplace transform will be this thing here. Second one, also you can see it's quite simple. A plus I omega plus S at the bottom. That will be the denominator. Okay. Okay, so now we'll just do again partial fraction. Okay, partial fraction. So we'll need to multiply this with this. Okay. So it is the complex conjugate, multiplication. So I don't feel like doing too much of that today, but okay. Okay, I'll just multiply it for you. Okay. Algebra I'm not very particularly a big fan of, but okay. I omega S. Alright, so a plus I omega is the complex number. So let's have it. Okay, a plus you have s squared, so we can apply the a squared plus 2ab plus b squared formula. S squared will be in front. Then you have the a minus I omega and a plus I omega. Okay, so that will give you a square plus omega square. So I will do it like this: a plus I omega, a minus I omega times a plus I omega. That will give you a square plus omega square. So a minus I omega times s. So that will be 1 s a minus I omega. Then I'll add also s a plus I omega. Alright, so that's how I do it. Okay, and again, any careless mistakes, just let me know. Okay, so what do we have in the denominator? We can just have s square, a square, or s square plus a square plus omega square, plus, okay, s, we have a 2as term here, so 2as. So s I omega, s plus s minus I omega, and s plus I omega, that will cancel out. Okay. Okay, again, let me reiterate. As and as will add up. These two numbers will add up. S I omega and s plus I omega. Okay, s minus I omega and s plus I omega, they will cancel out. So these two terms will cancel out. So now we can see s squared, 2as, a squared, and omega squared. So this is a basic formula, which is s plus a squared, s plus a whole thing squared, plus omega squared. So this will become our denominator. Okay, so I will just say note. Alright, so this is how we expand out, and the top is pretty simple. Okay, substitute back. Okay, so we will have this whole long thing as the denominator here for both sides. Let's see whether it's built properly. Yes. Okay, now the numerator will have to change. Okay, so the first one will have a plus I omega plus s. So let's do a plus I omega plus s. This basic partial fraction thing. And I'll just do it to the next side. A minus I omega plus s. Okay. Now that we've gone through all the math, which is not particularly a killer, but it's well, it is what it is. Okay, we'll notice this a in the first term will cancel with a in the second term, s in the first term will cancel with s in the second term, but I omega in the first term will add with I omega in the second term, because minus minus will become a plus. So we can just write it like so, like this, 2I omega, and very conveniently that will just give us omega. So this is how we do it for sine wave. Okay, Laplace transform of this this exponential decaying sine wave. Okay, if you check Wikipedia out, this should be what it is, right? This should be, oh, wrong one. This should be what where's this sine wave? Okay. I'm pretty sure you can do the same for cosines as well, but I'm not going to do it here. Right? You can go figure it out. Alright, but the principles are all the same. You can just expand it out. And basically you're done. Okay, so thanks for watching. See you again. Bye bye.